Okay. Hi, everybody. I think you can start now, 3 p.m. So let's go. My name is Stefan, and today we'll talk about how profile guide optimization makes your code faster without requiring any code changes from you. First, a little bit about me, and don't want to waste too much time with it, but like I said, my name is Stefan. I work at G Research, which is a company working in finance. Hence, performance is quite important to us, and hence why I'm talking about that. And that also means I'm not a compiler dev, so we'll talk about a lot of compiler things today. If you're a compiler dev and maybe I missed a little bit, then please point me out. Cool. First, I want to start with a poll to kind of like get a bit of an idea of what the audience has used so far. And the poll should be started now. And just please vote whether you have used link time optimization, LTO for short, or maybe you have even already used profile guide optimization, PGO, or you've used none of the two. LTO is not part of this talk today, but it's something that is, I'd say, very often kind of like mentioned in the same context. And yeah. Okay, I see quite a few people have used none of the two, which is great. Means you will definitely learn something new in this talk. I see somebody has already used LTO. That's good. It's maybe a bit easier to deploy than PGO is, but nobody has used PGO. That's great. So lots of new learnings today. I'll end the poll here. I think we've got a good picture. Cool. So first, I want to kind of like describe the problem that PGO is trying to solve. If you have an optimizing compiler, and that's basically all the major compilers like GCC, Clang, MSVC, then the compiler does optimizations, right? But very often the compiler is in the situation where it maybe cannot do an optimization because it's not entirely sure about something. I have this small code sample here. So it's kind of just some pseudocode. We have a send function. You could imagine sending something on a socket. And the send function returns an error code, EC. And obviously, we need to handle this error. So we have this if branch, if EC, then we do some error handling. Otherwise, we just continue. And now we, as a human, can kind of like know or guess that this error case is probably very unlikely, right? During the normal case, you will never have an error. You will just happily send. But the compiler can't really know that. Compilers could apply heuristics, like let's assume you have something like Go or even Rust, where you have maybe an error type pretty close to the language. Then the compiler could, for example, always assume that a branch, which just checks for an error, is actually unlikely to be taken. But in something like C++, we don't have that. So the compiler here simply might not optimize for the good case because it doesn't know what the good case is. And this problem is what PGO is trying to solve. So how does PGO do that? It simply, as the name suggests, does by being profile guided. Very often, some other people also use the name like feedback-driven optimization, but it's basically both is the same. How does it work? In general, and this, like in this talk, we will focus on GCC, but the same principle applies to all the other compilers. You basically compile once, and during this step, the compiler doesn't like give you a fully optimized binary, but it gives you an instrumented binary. And you can then run this instrumented binary, and during the runtime, it kind of like tracks maybe like, is this branch being taken a lot? Is it not being taken a lot? And then in the end, it writes out all this instrumentation data. And then we come to the second step, to the second compilation step, where you compile your program again. And this time the compiler can make use of this instrumentation data that you've previously generated and can then make better decisions. So if we go back to our example here, for example, then I've kind of like annotated in blue, which is basically the data the compiler then has. So the compiler knows, okay, during runtime, we took this branch maybe once, like when you close the connection or something, but 10,000 times we didn't take it because we're sending happily. And now the compiler knows this branch is not important and it can optimize for that case. So much for the theory. How it sounds kind of simple, and it is basically. How does it look in practice? And here on the slide, you basically see how you can use PGO with GCC. How do we do that? at first we have G++, and then this is the important flag, minus F profile generate. So what this does, we create a main binary with our main CPP file, and this will create a main binary which is instrumented. So then in our second step, we just run main. And I have this comment here, run binary with some representative input. We'll come to it in a second. That's very important. And what that will do is it will create this main.gcda file. And that's simply a GC specific file, which contains all this profile information, this instrumentation data from the run. And then we compile a second time, this time with F profile use. And GCC will automatically know, okay, there's main CPP, so I'll look for main.gcda, and it will use that for optimization. You can obviously like specify where to put these files and all this stuff, but fundamentally it's just this. So that's all you need to do. Maybe you will have to adapt maybe your CI a little bit to kind of like compile twice, but there's not more to it than that. The only real important thing is this comment which I have here, to run the binary with representative input. Because obviously, as you might imagine, if we train the binary on wrong input, then the compiler will optimize for the wrong cases. So what are good things to use for testing? And from my experience, generally, if you have, for training, but from my experience, if you have good testing for your application, then you will have an easy go with this, because you can use these kind of tests for PGO training as well. What kind of tests? Integration tests are very good. So maybe like a system test, which, let's say, I don't know, let's say you have a DNS server, right? So you just have a small integration test where you send a bunch of DNS requests to your DNS server, and the binary is instrumented, and then it just goes through the main paths, right? That sounds very simple, but it is that, because what PGO is generally about is about your whole binary. It's not about like one hot loop making that super fast or something. It's about many small optimizations across your whole binary. And again, if you think about branches, you probably have in the application like lots of branches, maybe for special cases where like certain, I don't know, requirements in your business area require just in one case, you know, like this little if branch, but you don't want to optimize for that. And that's why integration tests are good. Similarly, if you have something like replay tests, so what are replay tests? Again, let's assume you have a DNS server, then in a canary instance, maybe you record in production all the requests that go into your DNS server, and you can use that then whenever you make a code change, you basically just replay all these requests from production against like an old version and new version, and then you compare like which output did your DNS server actually generate. And this can be used for PGO training as well, because think about it, you then exactly run kind of like with a production workload, and that's what you want to optimize for. What else can you do? There's something I will not talk about in this talk, but GCC also supports a mode where you can actually profile it. So you could profile a canary instance or something and use that data for training. It's similar, right? Because then you know, okay, which paths did I take? But the instrumentation way is generally better. One warning maybe, like don't use unit tests, because unit tests are exactly not what you want for PGO. In unit tests, you want to take all these edge cases, you want to test all these error cases, but that's not your common case, right? The common case is what you have in an integration test. Right, so to summarize this, I think from my experience, getting good training data is actually not that hard if you have good tests. And if you don't have good tests, maybe you should start with that first. Now, so much for theory, like what performance gains can we actually expect in practice? And for that, I quote a few like major projects. Like I said, PGO is generally useful with large projects. Chrome is a large project, obviously, lots of code. And Chrome employs PGO, and they got 10% faster page loads, which is quite nice, right? They didn't have to manually optimize anything. Obviously, 10% is maybe not like the super optimization, but like I said, this is across your whole program once you have a saturated program. And more results, Clang itself, so not compiling like a program with PGO with Clang, but Clang built with PGO, and they reported 20% faster compile times. I think that's great, something in C++ heavily needed, which is so slow at compiling. 20% is a lot of man hours saved. Now, so much for the intro. That's how I use PGO. And now I want to go to a demo bit. So what we'll look at is a few code examples I came up with. They're obviously kind of like made up, but they will show a few scenarios where PGO is useful and which optimizations PGO does. So we'll generally first look at the code, then look at the assembly, we'll look at the baseline, like non-PGO optimized version, and at the PGO optimized version, and then also have a look at the performance. Right. I have 3 examples. And the first example I want to look at is hot-cold function splitting. So I hope in a bit you will understand where the name comes from, but let's first things first. Let's have a look at the code. So this is our main function. It's maybe a bit ugly, not the cleanest C++. We include these CPP files that simply generated code, which I code generated, so it was easy like that. Why do I generate code? Because like I said, many PGO effects only come into effect when having like large binaries. So we need, like a lot of functions. And that's why I just generate like thousands of functions. What do we do in this example? We have a main function. We have some runtime input, right? That's very important for PGO. It needs to depend on some data. And we simply pass a flag. The flag is true if we pass 1, it's false if we pass 0 or anything else. And then we have this value, which is just some value we'll do some math on, magic value. We have this loop, again, like do some work. Actually, in this loop, we call all these calls, and finally we print the value just to not get it optimized away. How do these calls look? We'll have a look at calls.cpp. It's lots of functions. Doesn't matter. It's just for code size. And how does the function look? We look at the definition in a second. We take this value, we add whatever this function does with the value to the value again, and we also pass the flag. That's very important. Now, the most interesting bit is how do these functions look? And we have, like I said, lots of them. They don't really matter. What matters is the structure. The structure of all the functions is the same. They just use different values. And don't try to understand the actual code. It's irrelevant. It's just the math to actually do some work. What I want you to focus on is the structure of this function. So like I said, we get an input value, we get a flag, and we return a value. And what do we do then? In the beginning, we have an unconditional bit of code. So we always execute this bit of code. Then we have this if statement where we check the flag. And if the flag is true, then we execute some additional bit of code. And after that, in the end, we again execute some code unconditionally and finally return the value. So what I want you to keep in mind is the structure of the code. We have unconditional code, then a bit of conditional code, which is conditional based on the flag, which fundamentally comes from runtime. And finally, we have some unconditional code again. So much for the code for now. And now let's have a look at that. So I have this build script, and this should now maybe be slightly familiar to you based on the slides. We first compile our base version. I call it the base binary. This is simply compiling the binary, no PGO. We'll use that as a baseline to compare against. And yeah, we compare with full optimizations here. And then we compile again. Like this time we try to generate our PGO binary. You should know the step by now, passing -f profile generate. We generate the PGO binary, and this now compiles our instrumented binary. This is not the final binary. This is the binary we'll use for training. It takes a while. Like I said, it's lots of code. Gives me time to drink something, but actually we're done. And you see here, we run our binary with 0 input. We print some control value, and we finally compile again with f profile use. So just to remind you what the 0 flag actually means for our code at runtime, it means this flag will be false in all the functions, and it means we'll actually not execute this code, right? So we'll not take this branch. Right, let me drink a bit. Right. Okay, now we have 2 binaries, the base binary and the PGO binary. So let's first have a look at the assembly of the base binary. Unfortunately, we can't use Godbolt here because of the 2-step compilation process, but you will not need to understand any advanced assembly. I'll try to point out the important bit. I use this object alias, which is basically just running object dump with a bunch of flags. Object dump is in disassembler, which basically allows us to look at the binary in assembly. Okay, let's look at base. What I want to go is like have a look at one of those functions, right? Let's go to func1000. We call it somewhere, and it's defined here. Now, again, don't try to understand the actual assembly. That's not important. What's important is the structure of the assembly you want to look at. And how does it look? It should look pretty familiar. We have, in the beginning, we have this bunch of code, which is being unconditionally executed. Then we have this test and jump equals. So this jump equals and test, this basically implements our branch, similar to the if statement in the code. And ObjectDump is actually so nice to annotate the jump for us. So we see here this kind of like jump marker. So what do we see here? This is basically the conditional code, again, which was in the if branch previously. And what we see is that if the flag is false, so we don't need to execute the code, we just jump over it and jump to the end here. And we finally then have some unconditional code again. Right. So I hope this makes sense. And I think the important point is that this pretty much mirrors the source code, right? We have unconditional code, conditional code, unconditional code. And that's the same both in assembly and in actual source code, right? Now, more interestingly, what happens in the PGO case? Let's have a look at that. Go to Func 1000, need to jump a bit, and here we are. So the first thing you might notice is that Func 1000 now actually fits on one screen, right? Previously, I had to like scroll around to put everything on one screen, but now everything fits on one screen. So some code is gone. And the second bit you might immediately notice is that there's none of these jump markers anymore. So let's have a look at in detail. Again, in the beginning, we have unconditional code, right? That's something we need to execute. And then we have our if branch again. But this time we have a test and then a jump not equal. And what we do here is, if the flag is true and we want to execute this additional bit of code, then we actually now jump to somewhere completely different, to a completely different address. So you see like here we had address 4787 and we jump to like 433E. So the code is moved away. But if we don't need to execute this bit of code, then we just continue with the unconditional code in the end. Now, why is this important? And there's two things why this is very important. First, let's summarize what happened. Basically, originally we had a jump, which just jumped over a bit of code if we don't need to execute that. With PGO, and knowing that it's very unlikely that we are taking this branch, so it's very unlikely that we need this additional bit of code, the compiler actually moved that code away to a different place. What does this mean in practice? First, our code is now a lot more compact, right? I think if you think about like optimization and caches and these things, traditionally people have a good idea when it comes to their data, right? They know, okay, I need to lay out my data in memory such that like data which I need to use together is also close together, right? People have an idea for that. But the same is true for the code your CPU has to execute, right? Which I think makes a lot of sense. The CPU needs to load the code, it needs to decode that code, and it maybe also needs to cache the code because we might come back to this code. And that's why the compiler has moved this unimportant bit of code away. Like, we don't want that. Now, when we load this bit of code, and you know, like if you load something from cache, usually you load a cache line, so you might load 64 bytes at a time. When we load this code, we might directly load this other code already. Well, previously, we might have polluted our instruction cache. That's the cache where you cache instruction data with additional bit of code that we actually don't need, right? So now we're a lot more cache efficient. That's the first step. Also, if you think about like speculatively execution, and then it also matters because here we have a non-taken branch, right? In the likely case, we execute this bit of math, and then just after we execute this. So what this means is if the CPU arrives here, it can like speculate across this jump. Okay, I'll like speculatively execute this bit, and that's good because we actually need that. In the previous case, we would speculate into some code that we actually don't need. And untaken jumps on the CPU level are generally very cheap. Like you can have lots of those. So that's why it's good. So these two things is why this matters. We are better in terms of like branch prediction and in terms of like instruction cache usage. We can also have a look at the kind of like where we would jump if we would actually need to execute this bit of code. And it's kind of like the same name, but it has this kind of like attribute clone.cold. So the compiler basically moves all the cold code, the code it doesn't need, to kind of like a separate place. Here we have, this is this clone cold bit, which is the additional bit of code. And you can see that like all the other cold functions are there as well. So the compiler moves all the cold code away so that it doesn't pollute your cache. Yeah, there's also like other kind of like, let's say, more instruction level optimizations, but we don't want to focus on these here. Right, so you could say, well, that's good talking, nice theory. Maybe let's measure this, right? Can we actually confirm what I've just talked about? And we can. So for that, I have a test script and I'll run it first. And there's a lot of output, but I will go through it one after the other. So we run the program under perf. For those of you who don't know, perf is a profile on Linux. So it can just profile your application. You get a stack trace, see where does your application spend most of the time. What you can also use it for is to measure performance counters on the CPU. What is a performance counter? A performance counter is basically a small counter on your CPU. So whenever a certain event happens, for example, let's say you load something from cache or you miss while loading that, then a counter gets incremented on your CPU. And you can read those values from your application, from user space. So you can see, oh, my application actually wastes a lot of time with cache misses. And that's what we do here. And in the end, we also see minus R3. So we run the binary 3 times just to get kind of like a bit of a baseline. And yeah, we run base and with our test case of 0 flag. Now, what do we see? Let's first focus on the bottom here. The average time it took our binary to execute in the base version was .206, while in the PGO version, it actually was .17. So we see a massive improvement. This is obviously a lot bigger an improvement than what you will see in an actual application. It's a micro benchmark, right? Keep that in mind. Can we also confirm the things I spoke about? And we definitely can. So for example, we have around 52 million branches we took in the base version. Out of those, we almost had 8 million branch misses, while in the PGO case, we had a similar amount of branches, but we only missed 30K times. So we have massively reduced the amount of cache misses. Good. Similarly, we have 300 million L1 iCache loads. So L1 is the first level cache, and instruction cache is the cache which caches instructions, which is what I explained before. And here we have also almost 6 million misses while doing that. In the PGO case, we all have like 130 million accesses and only 1.5 million misses. So we see a massive improvement here, right? That confirms what I spoke about before. The effects we can see in the assembly, we now actually see on the CPU. Right, and to summarize, why hot-cold function splitting? Because we split the function up. We split the hot bits, the code we definitely want to execute, away from the cold bits, which we might maybe need to execute, but very likely not. Cool, and now I want to go to the next example. And this time we'll talk about hot-cold function relocation. That's clear. And let's have a look at that bit of code. Okay. Again, we have this main binary. Maybe the structure's familiar to you by now. We take, again, the flag, runtime input, the flag, right? And then we have this value, which we do some math on. And here we have a loop. That's the important bit. And in this loop, we have an if statement. If the flag is true, we call all these warm calls. I've already kind of like shown by the name that this is the case we will take. And otherwise, we call it cold calls. Let's have a look at those. Let's just look at warm calls. Here you see, again, the similar structure, right? We need a bit of code and we have lots of hot functions. So the thing I want you to remember here is that all these functions are basically hot 1, hot 2, or 3, right? But we don't calling them in their numerical order. So we call hot 1749, hot 1362, and so on, right? It's basically random. We're not calling them in the actual order in which they're defined. How are they defined? You can have a look at it as well. Should be familiar by now, some math just to get some code. And we have hot 1, and then we have cold 1, then we have hot 2, and then we have cold 2. So this is what you should keep in mind here, that the order in which they are defined is numerically and always hot, cold, interchanged. And the call order is either all the hot functions, but in a random order, or all the cold functions also in a random order. Now let's have a look at the assembly again. Well, let's first build it. Same story. That gives me some time to drink. Also, maybe one thing to point out while this compiles, these names like hot-cold function splitting, hot-cold function relocation, they are like, there's no official dictionary where those are defined. but generally people understand them and they're used in different places. But yeah, like function splitting is, for example, a general term. Okay, this takes a bit more to compile. Again, we have lots of code. Yeah, we train with PGO1, so this means we'll take all the warm calls. And print some debug value, and then fprofile use again to get the final optimized version. Now let's maybe run the test first. Doesn't matter which way we look at. Again, we see if we look at the pure time it takes, we see the base version takes 0.2 seconds, while the PGO version takes 0.08 seconds, right? So again, massive improvement, obviously a lot more than what we'll see in practice. We see we again have reduced L1 iCache loads, almost a third only. We have a lot less misses. And yeah, something I didn't talk about before is these stalled cycles front end, stalled cycles back end. So in general, how CPU works is there's a front end, which is tasked with fetching the code you want to execute it, decode it, and feed it to the backend. The backend is the bit which is actually responsible for doing useful work, right? To like execute all the math and stuff. So basically, if the front end is too slow, the backend can't execute stuff. And we see that we have a lot less stalled front end cycles as well, and even backend cycles. Right. So from a pure performance measure, we see the optimizations we did are good. So let's have a look at what the compiler actually changed here. And for that, we'll have a look at the base version. And let's go to hot one. Actually, yeah. So this is the first function we call, right? If you remember back. Now, how are these functions defined? There's a bunch of code. Again, it's not relevant. Now, what is relevant is that we see in the binary, the functions are defined in the same order in which they're defined in the code. So you see that we have cold 1748, then we have hot 1749, and going down, we then have cold 1749, hot 1750, right? So this is the same, again, maps directly to the source code. They get compiled exactly in the order in which they are defined in the source code. Now, what does PGO do with it? You might have an idea already. And here we are. We see it does some splits the main bit out in the loop. This is called function splitting. We know that already. What we want to see is how is hot 1749 defined? And here we go. So we see it's in this section is the first function. And then we go down. And what do we see? There's no cold function in between. But even more interestingly, the compiler has actually also reordered all the hot functions. So now the functions are in the assembly in the same order as which they are being called. You have hot 1749, hot 1362, and if you look back at warm calls, that's exactly the order in which we call them. And so again, why did the compiler do that? And this comes back to instruction cache usage. What happens when we run this program? We need to call all those functions, right? And what does this mean? We jump to this address. We need to load this code. And what happens after that? Oh, we actually call this function. So again, once we've loaded this, we might have again already loaded a bit of this code. So once we've executed this bit, we come to execute this code, and we've already have it in cache because our code is now a lot more dense and compact. While previously, first, the functions were all in a completely different order. So we would jump around. We don't want that. And also, there was this call function in between the functions we don't actually care about, which is now no longer the case. So, and this shows why we have such a better usage of the instruction cache. Now you could ask, okay, but couldn't the compiler, couldn't it always do that, right? It sees there's all these warm calls together, all these cold calls together, and it even knows the order, so why does it not sort it by them? It's definitely true, like in this kind of micro benchmark mini example, it could do that. But if you think back into a real application where you have lots of if statements, lots of functions, which might not be called straight after the other, but if flag 1, execute function 1, if flag 2, execute flag 2. And at that point, the compiler can't know, right? At that point, it needs the PGO data to know which functions are actually being called frequently, and then it can look at the order and sort them by that. While in this case, it's just not worth it without having the extra bit of data. Cool. Right. So far, these functions have mostly, these examples have mostly focused on, like optimizing the layout of your binary. But that is a major part of PGO, which is, as I've mentioned many times, is that you need to have a large application. These kind of effects don't matter if you have a small application, because then, like, if you have just one function, it's just in cache, right? It's hot, and even if there's like one other function, it's also in cache. It's fine. Now, as a third and final example, I want to look at a case where we actually see a different effect for PGO, and that is called devirtualize. And again, we'll look at some code first. So how does devirtualize look like? As you might have guessed, some virtual functions are involved. We have this iCalculator class, and it has one virtual function, and abstract virtual even, so it's kind of like an interface, which is why it's iCalculator. And then we have two implementations. We have the multiplier implementation, which implements calculate, final, all good. And as you might have guessed, it takes the input and multiplies it by OX1234, which is just a magic value so that we can easily see it in the assembly. Similarly, we have the divider class, and it also implements calculate. It has to obviously, but what does it do? As you might have guessed, divides by the magic value instead. Now, what do we do with these classes? And again, we have our runtime flag again, our command line flag, and that we use to instantiate the calculator. So if the flag is true, this is the case we will have in our example, we will create a multiplier. If it's false, a divider, right? I think that's a common example where maybe you have some visual class and then in test you create iTest interface, while in production you have the actual like implementation of, for example, a socket or something. What do we do with this calculator? We just call calculate, so that's yet another calculate function. This is simply just here to kind of like limit the assembly that we want to look at to this very simple function, makes it easier to look at. But what do? We simply pass this calculator pointer and the input and call calculate on this interface with the input. Cool. Now there's no other code to find here. We can simply build it again. Builds a lot faster this time. Not much code. We train it with one. Like I said, this means we have the multiplier case, and we print this debug value, and then we can also run it. And what do we see? We again see our debug values. We see that we are a lot faster again. So 0.024 compared to 0.017. So 30% improvement. Again, micro benchmark. And we see we take a lot less branches. Now, before we have a look at the assembly level, I first want to take a step back and talk a bit about virtual tables. So, because that's important to understand what then happens on the assembly level. There's no standard defined way of how you implement virtual functions, but a common way is to use vtables. What is a vtable? How do vtables work? If you have a class which has a virtual function, like an instance of struct multiplier or an instance of struct divider, then you have this hidden first member, which the compiler just generates. You don't see that. You obviously don't define that in your class, but that is there. And it's basically a pointer to a vtable. And this vtable pointer for the multiplier instance points to the multiplier vtable. Both vtables kind of look the same, but obviously what's the difference? They have this, I call it a calculate pointer. It's obviously not like that, but that's effectively what happens, which is basically for each virtual function, it has a member which points to the actual code you need to execute. So for the multiplier case, the pointer points to this address in code, which here, kind of like in pseudocode, is the actual code, obviously then in assembly and binary. Or for the divider, it points to a different address, which implements the division case. Now, what does the compiler do when it wants to call a virtual function on such an instance? It does basically two loads. First, it loads the pointer to a vtable. Then it knows, okay, I need to call calculate. It's the first member. I load this pointer again, and then it knows, okay, to execute multiplier calculate, I need to jump to this address. And we'll see this in a bit on the assembly level. I just wanted to refrain it because I'm not sure whether everybody's familiar with that. Cool. Now let's have a look at the base version, and we'll just jump to calculate, and here we are. So this is the calculate function. This should be a bit familiar. We pass the iCalculator pointer, and this is the value which we'll pass to calculate. And now this is probably the most complicated assembly we'll need to understand, but I will annotate it so that it's hopefully more understandable. Here we dereference what's kind of stored in this RDI register. RDI is the first argument you pass the function. So this is the iCalculator pointer, right? So we basically dereference where the iCalculator pointer points to, and it obviously points to the first member in the struct. So here we load the pointer to the vtable. Load vtable pointer, right? And then we have this vtable pointer in Rx. And again, we dereference this pointer and just jump to there. Now, this is kind of 2 steps in one, because in our vtable, if we look back here, we only have 1 member, right? So again, the pointer automatically points to this other pointer in the vtable. So we load pointer to calculate function and jump there, right? So there's 2 steps in one. We dereference and then jump there, and that's all this function does, because that's virtual dispatch. It just loads the vtable, then checks in the vtable where do we need to jump, and jumps and execute that. That's the base case. That also shows why people generally want to avoid virtual calls in important code, because we don't want to jump around. That's not good. We can also see the 2 implementations. So for example, we have multiply calculate, we see imul, and then we multiply by this magic value. We also have the divider. Division is expensive, so we don't want to directly divide. So GC does some magic here, which I don't even understand. But yeah, that's not important. And now we look at what happened in the PGO case. Let's go to calculate. Okay, sorry, a bit of jumping around. Right, this is what we want to focus on, right? Again, this is our calculate function. Now, which code transformations happened in here? In the beginning, we have the same code again. This is load pointer to vtable, should be familiar. And this is load pointer to calculate. Right? This time we don't jump there directly. We first load the address where we would jump. Why would we do that? And you've probably seen by this time that this is actually a lot more code now. So what we do here is we compare Rx, which is our pointer to the calculate that we will execute, to this magic value. And here we have a jump not equal. So if we compare this value, but it's actually not that, then we have this jump marker again, right? And we jump to this bit of code. And here we now do jump Rx. So what we basically do is here jump to calculate, right? But we only do that. This is, again, how the base case works. We only do that if our comparison with our magic value doesn't work out. And now let's have a look at what happens if we actually find this value to be true, this comparison to be true. So they are equal, then we don't jump here. And what do we see? We have an imul here. So what the compiler did is it inlined the I multiplier case, because it knows that the multiplier is the likely case. So again, very likely we will have a jump here, which we don't take. Remember back, non-taken jumps are generally very cheap. And we just have the code inlined, we then want to execute, and we return. So why is this good? Very easy for the CPU, speculate across, execute this bit of code, and return. So I really like this example because I think it shows what this extra bit of information can do. And this is also the kind of bit where you could ask, oh, why does the compiler not just do that always? Like, could it not just add an extra step for the divider? And of course it could. And I think even if you train on both, it actually does that. But why does it not always do that? And the problem is that it just doesn't generalize, right? You could imagine you have like 10 implementations of the iCalculator interface with all the other math operations or something. And then you come to the point where having like lots of jumps is actually more expensive than having just your jump table, your default jump table approach, which then is just really good, right? You have many different things, you want to jump to them, and then it's great. But without this extra bit of information, the compiler can't do this optimization. Cool. These were the 3 examples I want to go through. Now, to kind of like give you a final idea of why it's important to get the right training, I want to run 2 of these test cases again, but this time test them with the opposite data that we trained on. So for example, in the virtual case, we run cold tests. And what we see now is we pass base equals 0, PGO equals 0. So if you look back, this now means the flag is faulty and actually use the divider instead of the multiplier. And this is not the case we trained for. And we see that immediately, right? Now our base case is with .003 is actually a lot faster than the PGO-optimized one. Why? Because we optimized for the wrong thing. So it's important to keep your data right. And that shows that. And we see that the same, right? We have lots more stalled cycles. And yeah, we can do the same with hot-cold functional splitting and do a cold test here as well. And right, this time, we pass 1. So what does this mean? This means if we go back to the code, should have done this before, but now just to get back into memory, we actually take this branch, right? But what did we actually do? We trained for not taking this flag, and we see the effects base version now faster with .34 compared to .39, right? So it's important to get your data right, but also like don't be worried about training on the wrong things. We'll see in a second how we can actually avoid that, but don't worry about it. PGO, like I said, is about massive amount of code, right? If you you will very often have this bit of code. If you think like, how often do you have if the bug level equals info, then print this, or things like that. Or like I said in the beginning, if error, then do that. And you might get it wrong once or twice, and that will be a pessimization. But as long as you get it right 90% of the time, you're generally good and you will see an improvement. Cool. Now, that we have looked at these examples, and I just want to go through a bit more, few practical things just to help you if you actually want to deploy PGO. And missing profile data is one thing that GC complains about by default, which is good. Finally, a sane default. So if you use profile use and then GC wants to compile foo.cpp, but it doesn't find profile data for foo.cpp, then it will complain and will issue an error. So if you compile with W equals error, then your compilation will fail. You can obviously work around that. If, for example, let's say you have a build process where you also build some test data, which you're then actually not training on. So you could have something like that, and you can then pass -W no missing profile, which will make GC ignore this case. It's obviously not good because you might actually miss a proper improvement. So probably look at that. If it turns out, yeah, that's fine, my build process is not entirely clean, then you can apply this flag. Multi-thread programs we haven't looked at yet so far, but you can use PGO with that just fine. You need to pass a few additional flags. They are just used in GCC to kind of like make the counter updates it uses atomic. And similarly, in the final step, -F profile correction, we also use that to account for that, something like that. You can also pass prefer atomic, which if you pass p-thread, will then use the atomic updates. And now this is something I already touched on. If you're worried about training on the wrong thing, obviously, like, just run your performance tests. That's always the true answer. If they are better, then that's good. But if you're worried about that, and there is certainly, especially if you use tests for training, there is things that you will run during training that are actually not important during production runtime. It could be things at startup, maybe setting things up, or like I said, training stuff. And you can tell GCC to ignore such files, or just include the files you want. For example, with fprofile filter files, and then you can, for example, just pass all your source files. This will make GCC only consider these files. Similarly, you can use fprofile exclude files, and you could just exclude all your test files, which will then make GCC ignore those. If, for example, you just want to exclude a certain function or something, there's also an attribute, no profile instrument function, and GCC will ignore that. Untrainable functions. So similarly, it could be that there is simply a function which you can't train. And for example, let's say a certain branch in the code which applies to certain hardware, but you can't train on that hardware, things like that. Then you can pass -f profile partial training. This flag is quite a wider impact because it will mean that for all the functions for which GC doesn't find profile data, it will basically consider them as if PGO was not used on them, right? So those are being optimized as normal, so to say, and they're not being pessimized as cold. And this is kind of like a final slide because people will probably ask about it. Likely and unlikely is a thing which I think is now even in standard C++20, I think, as an attribute. What does it do? You can instrument if branches, for example, as likely or unlikely. So you're kind of like telling the compiler, oh, this is a likely branch. And in the very beginning, we talked about this error case. This is something we could do, but it doesn't scale, right? You can't annotate the 12 billion branches in your code. And similarly, this gets stale. Similar to comments, this might also get stale. Somebody might change how the flag behaves, simply just inverts it to something and changes the code, but doesn't change likely to unlikely. And then you've pessimized. This is something you don't want to do. So just use PGO. And actually, if you use PGO, the compiler will ignore these annotations. Right. And kind of like to finish this off, sources for the material. Like I said, this talk was mostly focused on GCC. Clang is very similar. It has a few different flags, but the fundamental principle is the same. And it's also true for MSVC, just compile twice, train in between, and it does the job. Another project I want to mention, Bolt. There was nobody here who has already used PGO, but if once you've used PGO, Bolt is kind of on top. It's a project by Facebook, which further tries to optimize the layout of your binary. That's something we saw in the first two examples, where the optimizations were very much concerned of how do I lay out my code. And that's something Bolt further tries to improve on. Also, one thing I want to mention is that PGO and even LTO are still under, let's say, I mean, heavy developments, maybe the wrong term, but they still get improvements. If you look at the changelog from GCC, for example, there is very often mention of improvements to PGO and stuff. I think there's also one guy working on Firefox who always compares like different compiler versions at like the improvements of PGO and LTO on Firefox. So there's still improvements being done here. So if you use that, you might even get even more improvements in the future if you use it. Yeah, that was most of my talk. Now we still have about 10 minutes for questions. So you can either ask here or further, I will also be in the Gather Town or on Discord, I'll say Slack. There's already 2 questions, so I'll start with those. Which kind of profiling method internally is used? Instrumentation, sampling-based profiling, you see, right? So you can basically use both. What we've looked at here is the instrumentation way, where we really compile it twice and the binary is instrumented. And then we say, we write out these extra files. But like I said, and that's something I didn't touch in this talk, you can also use a sampling-based way. And for example, I read the other day that the Clang guys are really trying hard to get PGO into the Linux kernel, and apparently they wanted to use the instrumentation way, but then the Linux people would rather prefer the perf profiling way. So both ways are possible. I think prefer the instrumentation way. That's probably the more proto one. Are there any ML-based techniques or heuristics related to work done in generating profile data? As if the profile goes wrong, the form goes the other way. So I'm not sure whether there's any ML stuff being applied, but you could obviously think that that is maybe something that will come or people want to work on, because it's the training bit is very similar, right? And that's what ML does as well. You train on some input, and yeah. Maybe with ML, you very often have kind of like this bias problem, which you probably have less because it doesn't really matter whether your value is 5 or 10, as long as you take the same branch. But yeah, it's not sure whether I fully understand the second bit. As if the profile goes wrong, the performance goes the other way. Yeah, so that's definitely the case, like we saw in this cold test example here. You need to train on the right data. That's very important. Okay. Unless there's any other questions, that's it from my side. And yeah, I will be in Gather Town or just ping me on Discord. if you have any questions. Can maybe wait a bit, I don't know. Oops. Further away. Oh, sorry, actually, I was reading the chat, not the question. Okay, there's more questions actually. Is the CMake support? There is, I don't think there's specific CMake support. How we have done it in my case is simply just compile twice, right? You basically run the full chain. And that works, right? As long as you don't delete your artifacts, so that you don't delete the profile data, you can just compile once and then compile a second time. Maybe just add the second flag. That's fine. Is there anything like this on Windows that you're aware of? I haven't used the Windows version yet, but I know that MSVC is capable of using profile guide optimization. And I'm not even sure, maybe Chrome, when they were still using MSVC, they were using the Windows version. So yeah, like I said, that's definitely a thing. Cool. I think now I've seen all the channels. Cool, thank you. And I guess then we'll see each other in GatherTown.